Okay, welcome everybody. It's my pleasure to introduce Viral Shah. Viral is a postdoctoral fellow at Harvard University in Daniel Jacobs' group. He holds a bachelor's and master's degrees in civil and environmental engineering, and he received his master's and PhD in atmospheric science from the University of Washington. His primary research interest is in the study of the sources and chemistry of atmospheric pollutants by combining observations and chemical transport models with an eye to informing public policy and reducing the impacts on human health. Today he's going to tell us about results from the Winter Airborne campaign. Some of you were participants in that. And what's been learned from that about wintertime pollution in the Northeast. And I want to say that this work was recently published in GRL and it's gotten some attention. It was featured in AGU's Research Spotlight, and it was also an editor's choice in Science Magazine. Viral.
Thank you, Mike. Thank you all for coming. Thank you, Mike, for the introduction. I'm here to tell you about wintertime aerosols and what we learned about them from the 2015 winter campaign. And my focus is more on the air quality perspective, the chemical composition, the distribution, the sources of aerosols. And some of you in the room were part of the winter campaign. If you weren't, it was in 2015, C-130 campaign took place in the eastern US. The main objective of the campaign was to understand pollutant interactions in polluted interactions in polluted and coastal environments with a heavy focus on nighttime chemistry. And in winter, and this is unique because most campaigns take place in the summer. Summer is the more active season for air quality chemistry, but this was one of the first to look at winter. And that's what really makes it unique, and that has helped us to answer some long-standing questions about wintertime air quality. And two of the questions that I'll be talking about today deal with the sources and trends of inorganic aerosols. And when I say that, I'm thinking about sulfate, nitrate, ammonium, and the sources of organic aerosols in winter. And these results have been published over the past couple of years, 2018, 2019, and also by papers Jegle et al. And Schroeder et al. 2018. Now, during the winter campaign, I was at the University of Washington doing my PhD work, and that was kind of in the middle of my PhD. So I was working with Liad Jegle at that time. I moved to Harvard as a postdoctoral fellow just last year. So we know aerosols are extremely harmful to human health. Every year, more than 4 million people die because of breathing air which is polluted by aerosols, by high concentrations of aerosols. It affects the lungs, heart, young people, elderly people, people with pre-existing conditions, heart or lung conditions are particularly susceptible to premature death from inhaling air which is laden with aerosols. So it's a global public health emergency in one way to say, but it also affects the Earth system in other ways. It affects human well-being because it reduces outdoor activities, it reduces visibility. It affects the climate system because it interacts with solar radiation, helps in formation of clouds. It also has effects on the ecosystems because when the aerosols deposit to ecosystems, they can acidify freshwater systems, they can change the nutrient balance, and that can lead to loss of biodiversity. So it has much broader impacts than just human health. But the issue is that conditions are getting worse as far as air quality is concerned. In the past 25 years or so, the population-weighted global average PM2.5 concentrations have been increasing, and they're at about 45 microgram per cubic meter, which is 4 times the guideline of 10 microgram per cubic meter. So the situation is worse in places like India and China. In the US, things are much better. Just in the past 5 years or so, the annual average concentrations have dropped below the WHO guideline. So things are getting better, but this does not mean that we don't have to worry about these small concentrations, because even at these concentrations, every year in the US, 90,000 people die prematurely because of exposure to these low-level concentrations of PM2.5. So there is really no baseline. Safest concentration is 0, but this is a huge number. So conditions are getting better, but they're not getting better as fast as we would expect. And I'll show you in a few minutes a couple of reasons why that might be. So as I was saying earlier, aerosols are a mix of constituents. The inorganic part is sulfate, nitrate, ammonium. And the organic part, we call them organic aerosols. The 4 main constituents make up about 80% of the aerosol mass in the US. And these are the 4 big constituents we'll focus on in this talk. Sulfate, nitrate, ammonium are chemically linked. Sulfate and nitrate are acidic species. Ammonia is a basic species, so they kind of balance the acidic species. So we talk about them kind of together. The sources of aerosols are either primary, that means they're directly emitted as a smoke from fire, directly emitted aerosols, or they can be secondary, that means they're formed in the atmosphere. And the secondary processes, they happen in the gas phase, so the reactions taking place in the air, or they happen within aerosols or within cloud droplets, which we call multi-phase processes. The gas phase processes are mainly sun-driven processes, so they are much faster in the summer compared to winter. The same way organic aerosols have primary and secondary sources, but these sources tend to change with seasons. So in the summertime, sources of ammonia, like agricultural sources, are higher, while in wintertime they kind of die down. Biogenic sources, which are major sources, major precursors for organic aerosols, are also higher in the summer, but in winter they die down. In winter, on the other hand, sources just like residential wood combustion become more important. So the sources change from season to season, but also the chemistry changes from season to season. In the summer, gas phase chemistry is more important as there's enough solar radiation to drive those reactions. But in the winter, the multi-phase processes that are happening on clouds, happening within aerosol particles, play a bigger role. And these are the processes that we do not really have a very good handle on, and that's why the winter campaign was so important. Now, these differences in the sources and chemistry that happen between the summer and winter are reflected in the concentrations of aerosols measured at ground-based stations in the eastern US. So here I'm showing the population-weighted average PM2.5 concentration for summer and winter. And we see that in summer, the composition of PM2.5 is dominated by sulfate aerosols. Now, sulfate forms from the oxidation of So2, and the oxidation processes are faster in the summer, where sulfate concentrations are higher. Typically, the aerosol concentrations are higher in the summer than in winter. In winter, sulfate concentrations go down as oxidation becomes slower, but nitrate concentrations tend to increase. And that's because nitrate forms more efficiently at lower temperatures in winter, as well as when there is less sulfate around. So nitrate partially replaces the lost sulfate from summer to winter, but not perfectly. But this was the situation in 2007, and this is a common view of aerosol composition. But things have really changed since 2007. Especially the emissions of SO2 and NOx have gone down substantially. SO2 emissions have gone down by almost 65% in just a period of 8 years, and that's better emission controls and replacement of coal by natural gas to produce power. NOx emissions have gone down by 35%, and that's because of more fuel-efficient cars, better emission controls on power plants, and so on. And these have made a big effect on the sulfate concentrations in summer. The sulfate concentrations decreased by almost 70% in 8 years, in line with the decrease in SO2 emissions. Nitrate isn't a big component in summer, so NOx emissions did not matter that much at that time. But the winter conditions are completely different. So from 2007 to 2015, there's just been a 40% decrease in sulfate concentrations, much smaller than the 70% decrease in SO2 emissions. Yeah.
I'm surprised that the nitrate concentrations are much lower in since they're a biogenic source primarily, unless something has also changed in agricultural practices.
So the nitrate is a mix of biogenic and anthropogenic sources. And I'm looking at eastern US, so it's mainly anthropogenic sources, and they have gone down a little bit, as you pointed out, but they're not a big component.
I'm surprised that it's gone down so much compared to 2007. I can understand the SO2 and the NO and the NOx, but I just don't understand why the ammonia has gone down.
Oh, why ammonia has gone down?
Ammonia.
Oh, yeah, okay. Oh, sure. Right.
Did I say
You said nitrate. Okay. Right. So the thing about ammonia is, as I was saying earlier, sulfate is the acid and ammonia is the base. So the concentrations are kind of tied together. So when one goes down, the ammonium in the aerosol also goes down along with the sulfate.
The chemistry of the atmosphere has changed as well. The pH of the atmosphere has changed.
The pH of the atmosphere has changed, has probably increased, at least in the summer. And that's why ammonium has gone down. Right. So, but if you look at the winter, nitrate concentrations haven't changed despite this 35% change in NOx emissions. And now it turns out that wintertime concentrations tend to be higher than the summertime concentrations. And that's kind of the puzzle which I was very intrigued by, and that would be the first question I'll try to answer today. So why have wintertime concentration of sulfate and nitrate change so slowly compared to the emissions of SO2 and NOx? So before we answer that, let's look at the chemistry of SO2 and sulfate. Now, it's part of a cycle that includes gas species like SO2, NOx, nitric acid, and the two kind of primary parameters that I think control the cycle are oxidants, the availability of oxidants, and the pH, aerosol pH. So the oxidation of SO2 to sulfate happens through many processes, OH in the gas phase, H2O2 ozone, in the aqueous phase, which happens mostly on cloud droplets. It's the H2O2 oxidation that is more interesting. It's a very fast process. So if there's SO2 and H2O2 present in cloudy air, either one of the reactant, whichever is present in lesser amount, will get completely consumed in a very short time. So it's a process that is limited by the reactants. And it turns out in winter over the eastern US, H2O2, the oxidant, is typically the limiting reactant. So that controls how much SO2 gets oxidized to sulfate. And I'll show you more details about that. The formation of nitric acid happens from the oxidation of NOx. It happens in the gas phase by oxidation with OH, but also on aerosol, in aerosol water or in cloud water by the oxidation of N2O5, dinitrogen pentoxide, and that is again a multi-phase reaction. It's a reaction that we have studied, we don't have very good constraints on, and something that the winter campaign was kind of focused on understanding that reaction in detail. Nitric acid conversion to nitrate depends on temperature. Colder temperature means more nitric acid gets converted to nitrate, and higher pH also means that more nitric acid will get converted to nitrate. So pH controls the conversion of nitric acid to nitrate. pH also controls the conversion of ammonia to ammonium. It turns out that over the eastern US in winter, most of the ammonia exists as ammonium, so we're not too worried about the gas phase ammonia at this point. The further complication is that the oxidants and the pH are actually determined by the other parts of the system, so which creates kind of this feedback loops. So for one example, as sulfate concentrations would decrease, as SO2 emissions decrease, the pH, sulfate is acidic, so the pH would increase. And that would mean that more nitric acid can get converted to nitrate because of the higher pH. So now there are these feedbacks that will turn out to be important. Now this system, there's quite a few things that we do not have fully constrained in the system, and that's why it's kind of difficult for models to simulate nitrate. These are results from the GEOS-Chem model a few years back, published in 2012, and we are looking at nitrate concentrations. These are the observed nitrate concentrations versus the model nitrate concentrations in winter. And we see that the model overestimates nitrate concentrations by about 2 microgram per cubic meter, or about a factor of 2 to 3. This is just one example, a GEOS-Chem model, but there are a host of other models that have the same problem where nitrate concentrations are overestimated, and it's because the nitrate chemistry, especially the multiphase chemistry, is not very well constrained. Models also have difficulties in simulating the trends. So the CMAC model here can simulate the trends in sulfate concentrations quite well, but it does poorly when trying to simulate trends in nitrate concentrations. So nitrate is kind of a wintertime nitrate is an interesting topic, and that's kind of where the winter campaign comes in. It was a huge campaign, like most NCAR campaigns. We used the C-130. We are based in Hampton, Virginia, and we covered quite a lot of area in the eastern US. There were 13 flights overall, many of them night flights, and I know it was tough on a lot of people, the night flights, and we were on a kind of shift in schedule. Once we started at midnight, the other day we would start at 5 o'clock in the morning, and that was really difficult on the people there. On top of that, it was one of the snowiest winters in Virginia. One of the reasons we were in Virginia was the winters are kind of mild, and we can fly very easily from that. But it turned out the 3 weeks I was there in the field, we just had 3 or 4 flights. It was covered in snow almost all of the time. But it was a great campaign, and we learned a lot. There are quite a few instruments measuring aerosol particles composition, concentrations, surface area, volume, and so on, number concentrations. Gases, nitric acid, N2O5, SO2. The measurements that I'm using most are from the AMS instrument operated by Jose Jimenez's group at CU. And I've used the other measurements kind of to constrain the model in general. So to kind of figure out this wintertime chemistry, what we do is we combine the winter observations, that's the key, but we also bring in ground-based observations. There are these ground-based networks, CSN, CASNet, Improve, that are continuously measuring aerosol concentrations and composition throughout the US. And we use the help of GEOS-Chem model, which is a 3-dimensional atmospheric chemistry model. Many of you may be familiar with it. It's widely used in the community, and it is a community-based model. It's developed by its users. Kind of the maintenance of the model happens at Harvard University, the group where I'm working in now. And GEOS-Chem has been my primary research tool. I used it during my PhD for the winter campaign, and I'm using it now for my research as well. GEOS-Chem has all of these processes, the chemical processes that we have been talking about so far. It has representation of these processes. So it's an appropriate tool to try to understand wintertime chemistry. So there are a few improvements that we made to the model. And these improvements were we could verify these improvements based on the wintertime observations of nitric acid, ClNO2, and other gases. The main improvements are the rates of N2O5 hydrolysis, which are based on recent, well, not so recent, but decade back lab measurements, but they weren't part of the model. We put that in, and we could compare it against the winter observations, and they work out well. We could increase the dry deposition of nitric acid, which is also consistent with the observations. And we recalculated ammonia emissions based on the meteorological conditions that we encountered in 2015, which were kind of unusual. And all of these improvements improved the nitrate simulation a lot. And the biases that we had seen in previous simulations of factors of 2 to 3 were reduced now to about 50%. So the model improved a lot after making these changes. So you can see how the model performed with respect to the inorganic aerosols. So on the left here, I have the winter observations colored by the concentrations, and these are the model results along the flight tracks. And this is just showing the composition, average composition of the aerosols measured there. And we see a very good correspondence, very good agreement between the observations and the model. Model gets the average concentrations within about 15% of the observations. The model also captures the composition, average composition of the aerosol quite well. We find that sulfate, for the winter observation, is kind of the important species, but nitrate isn't that far lower than that, which is kind of consistent with what we saw with the surface observations. If you look at the vertical profiles of sulfate, nitrate, ammonium, we see that the model is able to capture these differences in these three species quite well. So the model is performing very well compared to the aircraft observations. We can bring in the surface observations, and the story remains the same. The model is able to get the average concentrations and the composition about right, which kind of builds the confidence in the model, and it makes it easier to use the model to probe the chemistry of sulfate and nitrate. And that's what we're going to do. So firstly, we found that sulfate formation is kind of inefficient in winter. Only about 18% of the SO2 gets oxidized to sulfate. And much of that, about half of that, happens to H2O2. Now, as I said, H2O2 reaction is limited by H2O2. So we can see that here. I'm plotting the rate of the H2O2 reaction against the ratio of H2O2 to SO2. And we see that the reaction rate increases as this ratio increases. So in this area, where there is more H2O2, the reaction rate is faster. So this area over land mostly is where the H2O2 is the limiting reactant. An increase in H2O2 would mean an increase in the reaction rate. We can think of it in a different way, or just a visualization of this. Imagine an air parcel with less H2O2 than SO2, and that it encounters a cloud, and SO2 gets oxidized by H2O2. The reaction starts. It stops at the point where H2O2 gets completely depleted. And the amount of SO2 that gets reacted is equal to the amount of H2O2 that was present in the air mass initially. So now if there's slightly less SO2 present, the amount of SO4 formed, amount of sulfate formed, would still be the same, which would mean that fractionally the conversion of SO2 to sulfate would be higher. So the oxidation efficiency would be higher because the amount of oxidant remained the same. And that turns out to be an important thing. As far as nitrate is concerned, we see that about half of the total nitrate, the gas and the aerosol, is in the aerosol phase. And that's because the pH of the aerosols is low. It's about 1.3. It's a fairly acidic aerosols. But there is large variation in the pH. So here I'm showing the fraction of nitrate that is in the particle phase versus the pH. And what we see is that as pH increases, the fraction of nitrate in the particle phase increases. So from a pH of 0, where only about 10% of the nitrate of the total nitrate would be as particles, at about pH of 3, almost 80% would be present as particles. The gray dots show the results from the GEOS-Chem model, and the black show the observations, and they match quite well. So we see this dependence of nitrate on the particle pH.
Can I ask
Yeah.
a question about that? So
Yeah.
I know you're not talking about sea salt here, but clearly there are some of those particles around, so you have a fair amount of sodium and chloride. Does the nitrate go in and displace the chloride in those aerosols?
It does.
Largely, or?
I don't know, I have a simple answer for that. It does, but at the coast, it's kind of a slower process. At the coast, we did not see much of it. When we went further offshore, we saw some displacement. So that's a process that happens. Also that it happens, most of the sea salt aerosols are in kind of the coarser mode, so bigger than 1 micron. And what we are looking at is kind of the finer particles where it does not play that much of a role. But that process is definitely important as you go further away from the coast. So the two main points that we were trying to make was, one is H2O2 to SO2 ratio controls how much, what's the oxidation rate of SO2 to sulfate. And second, the pH controls how much nitrate is formed from nitric acid. It turns out these two are important as we try to understand what's happening to sulfate and nitrate as SO2 and NOx emissions decrease. So I ran a couple of experiments with the GEOS-Chem model where I decreased the SO2 emissions from 2007 levels to what we would expect in 2023 based on EPA data. And we find that as SO2 emissions decrease, the ratio of H2O2 to SO2 is increasing, which means that there is a higher oxidation efficiency of SO2 to sulfate. So although SO2 emissions are going down, more of the SO2 is getting oxidized to sulfate, and the sulfate concentrations are decreasing far slower than the change in SO2 emissions. So it's the oxidation efficiency that's getting faster at lower SO2 emissions that's having an effect on sulfate concentrations. Now for nitrate, it's a little more complicated. As NOx emissions go down, we find that nitric acid concentrations go down almost linearly, but parallelly, sulfate concentrations have been going down, which means the pH has been increasing. So nitric acid, more of the nitric acid is getting partitioned to the particle phase, forming nitrate. So it turns out that these two effects cancel each other out. And the amount of the lower nitric acid and the higher partitioning of nitric acid to nitrate are almost equal. So when we see almost a 50% decrease in NOx emissions, there's almost no change in nitrate concentration. It's just these two effects compensate for each other. And the increase in pH because of lower sulfate is letting the nitrate concentrations remain flat. Now, if the NOx emissions had not decreased, then we would have seen an increase in nitrate concentrations. So it was good that the NOx emissions also decreased by 50%, and the nitrate concentrations remain the same because of that. If not, we would have seen nitrate concentrations increase because the pH is increasing. So to summarize kind of this part of the inorganic chemistry, we saw that based on the winter observations, we could constrain the model and kind kind of investigate the processes, and we find that there are these feedbacks between SO2 emissions and the sulfate formation efficiency, and sulfate concentrations, particle pH, and nitrate concentrations that are slowing the change in sulfate and nitrate concentrations in the past decade. And we project that will continue to do so in the near future, in the winter time. So let's move on to organic aerosols. Now, when we place organic aerosols on top of this picture that we saw earlier, we see that there is very little difference in the concentrations of organic aerosols between summer and winter. Now, we know summer is a season when biogenic emissions are high, which is a big source of organic aerosols. Biogenic emissions die down in winter, especially in the Northeast US. But there's still a lot of organic aerosols around. So what are the sources of this? What sustains these high concentrations? And as you see, there isn't much of a change in organic aerosol concentrations from 2007 to 2015. So now they're becoming a more and more important part of the total aerosol mass than previously. So let's look at this question. Now, organic aerosols, as I was saying, are not like sulfate or nitrate, where it's just one compound. It's a mixture of thousands of compounds undergoing thousands of chemical reactions. And the chemistry is very complex, and we don't really know much about the chemistry. This is kind of a very simplified representation of chemistry, which also most of the models have with some variation. Organic aerosols are classified by their sources. So we have POA, primary organic aerosols, which are emitted directly from sources like residential wood combustion, smoke, etc. And then there are secondary organic aerosols that are formed in the atmosphere from oxidation in the gas phase or in multi-phase processes. Now, each of these, SOA and POA, have their gas phase counterparts. We just call them POG, SOG. Most of the SOA is formed from the oxidation of primary organic gases which are emitted by industrial activities, cars, and so on, which oxidize to form secondary organic gases that have lower volatility. So they condense to form particles much easier. So the secondary organic gases form SOA, and this process is faster in winter. The condensation is easier when temperatures are lower. There is some formation of SOA within the particle phase, but we're not sure how important that is. Different models represent these processes differently. Some have more detailed chemistry based on laboratory work of a few selected species. Some have simpler chemistry. But there are a lot of assumptions that all of the models make, and there is a lot of uncertainty. It turns out that most of the models underestimate organic aerosol concentrations in urban areas. This is a compilation of 31 models, global models, and we see that almost all of them have a bias of about 50%. The median bias here is 62%. There are some models, there are newer models which do a much better job than this. But again, they make many assumptions. Some of them do not have very good constraints from lab or field studies. So we can bring in the winter observations again to bear in on this problem. What's causing this uncertainty? What are the sources? And we can tie in the ground-based observations and again the GEOS-Chem model. So for the simulation of organic aerosols in GEOS-Chem, I use a simple scheme which was developed by Jose Jimenez at CU, and it's an empirical scheme based on field observations in urban areas. What it does is it emits a primary gas in proportion to the emissions of CO from an urban area, and that gas gets oxidized to form secondary organic aerosols. So it's very simple. There are just 3 species involved. We have primary organic aerosol emissions from the NEI inventory. And the proportionality of the emissions and the oxidation rate were also determined from field studies. So it's a scheme that Jose's group has been using in campaigns, mostly in the warm seasons, summer and spring, and it works well. It hasn't been tested for winter, so we'll do this against the winter observations. There are other schemes in GEOS-Chem we could have used, but we tried them, and they do not give good results. So we'll use the simple scheme and see what we find with that. So here's what we find. So I'm again showing the winter observations, the model results, and the vertical profile. And we see that the simple scheme does really well in capturing the total concentrations of organic aerosols, which is within a few % of each other, and also the vertical profile of organic aerosols also captures the surface concentrations of organic aerosols quite well. So the scheme is performing well even in winter, although it was based on observations in the summertime. So now we can look at the sources. We can look at the sources in a multiple different ways. One of the ways that Jose Jimenez's group looks at the sources is by factor analysis. So they take the organic aerosol mass spectra time series, separate them into factors. One factor represents the chemical constituents which are more closely related to secondary organic aerosols, and they call that the fraction which is SOA. And they find that about 60% of the organic aerosols is secondary organic aerosols. We find the same in the GEOS-Chem model. About 60% is from secondary organic aerosols. And this was the unexpected result. The common view was, before we had the winter campaign, was that most of the organic aerosols in winter would be primary organic aerosols. In winter, residential wood combustion is a big source, and as you see, residential wood combustion makes up about 75% of the primary organic aerosols. Oxidation of gases in winter is lower, so we did not expect there to be so much SOA, but we did find it. And it seems that there might be compensating processes, although oxidation is slower. Maybe it's a condensation of the secondary gases, which is easier in winter, and that is enabling SOA to be formed faster. We don't exactly know what's happening, but the fact that there is 60% of it is SOA, and this has always been kind of a neglected component. People thought once we control the primary organic aerosol emissions, we will be fine. We don't have to worry about the secondary emissions, but that's not true. So let's look at the sources in a different way. It's kind of a Lagrangian perspective that aircraft observations are very suited for. So imagine an air parcel moving over a source region like a big city. As it moves, it picks up emissions of CO, organic aerosols, NOx, all sorts of things. And as it moves downwind, there are physical and chemical processes that go on that reduce, change the concentrations. Upwind of the source regions, CO and organic aerosol concentrations are low because the air is cleaner. As it picks up emissions, the concentrations increase. And as it goes downwind, because of dilution, the concentration decreases. Dilution is because of mixing of cleaner air surrounding the plume, and the concentrations go down. We can neglect oxidation and deposition on like shorter time scales of a couple of days or so. So this happens for CO, but for organic aerosol, there's one more process happening, and that is formation of secondary organic aerosols. So what happens is organic aerosol concentrations actually go down, but they don't go down as fast as CO concentrations. And if we take the ratio of the enhancement in organic aerosol to CO, we find that they would actually increase downwind because of the formation of a new organic aerosol, which is the secondary organic aerosol. And this is exactly what we find in the winter campaign. So I'm showing the ratio of the enhancement of organic aerosols and carbon monoxide to the photochemical age, which is related to the transport time, but it also takes into account the oxidation that is happening. And we see this increase in this ratio. It's about 30 near the source regions, where there is almost no secondary organic aerosols. And by about 1 day of processing, or 1 day of photochemical age, that ratio increases by a factor of 3. So this whole area, this is all new organic aerosol that is formed downwind of the sources. And that's formed because organic gases, which were emitted in the source region over here, are getting transformed to organic aerosols, and they're forming secondary organic aerosols. And we see that this slope at which new organic aerosols are forming in winter is very similar to that in summer. Again, which kind of brings in this consistency between the seasons, something we did not expect, but it seems that maybe the emission mix is constant between the summer and winter. Maybe there are compensating processes, more condensation in winter, although there is less oxidation. So there is this remarkable consistency between the two seasons. We put in the GEOS-Chem simulations, and we see that it captures this increase in organic aerosol with photochemical age quite well. It gets the right amount of organic aerosol near the source regions and the right amount further downwind, which means that the emissions as well as the growth because of secondary organic aerosols is well captured by this simulation. Now it also means that the primary organic aerosols that the model simulates, which is from the NEI inventory, is good, and it kind of verifies what the NEI inventory has. So the winter campaign observations can be used to do that as well. So now we can bring this together and kind of have a seasonally averaged view of organic aerosol distribution from the model. And we find that there's about 1 to 1.5 microgram per cubic meter of organic aerosols over the eastern US, and almost 60% of it is secondary organic aerosols. And that's almost everywhere. Previous measurements made in urban areas suggested that secondary organic aerosols may be more important in just the urban areas, but that's not really true. Even in rural areas, in kind of the more background areas, secondary organic aerosols are very important. And if you look at the POA, with the primary organic aerosols, you find that about 70% of the primary organic aerosols are from residential wood combustion. So that's another source, kind of a distributed source, that is important to consider in air quality management. So when we start looking at trends in organic aerosols, this picture kind of gives us a clue at the sources that we need to be worrying about. We do not really understand the chemistry of SOA. We don't know where it comes from. We don't know how it is formed. We just know that it's there. So there's a lot more effort that needs to happen to understand these sources, to try to understand the trends and maybe use that to kind of make an informed policy decisions about organic aerosol concentrations. But this is kind of a new picture that we got from the winter campaign. Yeah.
So the area around Georgia, you're saying that you don't necessarily know what it comes from, but looking at a concentration, that's obviously both emission and a transport velocity. So are there smaller velocity wind speeds when you're down in Georgia as opposed to up in New England in the wintertime?
I wouldn't say so. I think wind speeds may be higher further north. What's happening here is there's this gradient in solar radiation that is very sharp in winter. So there's more secondary organic aerosols. Yeah. So when we bring in the organic aerosols and sulfate, nitrate, ammonium together, now we have a more complete picture of the distribution, the concentration, and the composition of aerosols over the eastern US in winter. We find that the aerosols are kind of fairly uniformly distributed, with concentrations between 4 and 6 microgram per cubic meter in the whole of northeast US. And we see that all of the constituents make a sizable contribution. Sulfate, nitrate, ammonium, and organic aerosols each contribute between 20 and 30% of the aerosol burden. So from an air quality perspective, we cannot afford to ignore any of these constituents when we are devising policies for reducing aerosol concentrations. And just to summarize, we saw that the winter campaign, the observations were critical in placing constraints on some of these processes that we had less constraints on, and field constraints on these processes. And using that, we could use the GEOS-Chem model, which compared well with the winter observations, and we found out the feedbacks that reduce the efficacy of SO2 and NOx emissions, and the reason why sulfate and nitrate concentrations haven't responded as fast as we would have expected, just based on emission reductions. We also saw that organic aerosols, secondary sources, are very important and something that we cannot ignore when we are devising air quality policies in wintertime. So with that, I'll stop and happy to take any questions. Thank you. I think I have a microphone here. You have it, yeah.
Viral, thank you for an excellent talk.
Thank you.
It's very interesting. And it's really nice to see the results of one of our projects.
Yeah.
We have questions for Viral? I have one question for you. It seems that the biggest discrepancy between model and observations is off the coast over the ocean to the far north. Do you have any idea what's going on there, why that is?
Right, it's kind of difficult to say. It was one flight, and
Single flight.
It was a single flight, and the model did not capture the meteorological conditions that well, and it's very difficult to say based on like one flight of observations. But yeah.
I didn't realize it was just.
No, it was like it was one or two flights that was happening there.
Sure.
Was there a question there? Yeah.
Very interesting talk, thanks. I'm curious how you got the observation error statistics here, or the uncertainty. You just showed that some, with the bars, right?
Yeah, so those were not error statistics. There's a standard deviation of the observations, the variability in the observation. The errors are typically smaller than the variability in the observation at one altitude. Yeah.
The questions. Here's one.
So you mentioned the deposition of nitric acid. What was that was not, you thought that wasn't?
Right. So we used the
parameterization.
Right. So I mean, we did not really change the parameterization. We used the Vesely scheme in GEOS-Chem, and one of the things in the Vesely scheme is that at lower temperatures, the resistance to surface deposition, resistance to deposition at the surface is very high. So the velocity, the diadeposition velocity becomes too low. And we think for gases like nitric acid, which are so soluble and so reactive, that should not happen. So we just changed that temperature dependence, and we actually removed it. And that increased the diadeposition velocity quite a bit, and which gives the right nitric acid profile, actually.
So do you think there are other things in the model that need to be, are there other uncertainties or errors you identified that you think should be addressed?
I think one of the biggest one is ammonia emissions. It's kind of an uncertainty. We do not really have a very good handle on ammonia. It worked well here. I don't know if it will always work, but that's something we need to think more about and maybe monitor better, have better description models of ammonia emissions. It's a difficult source to estimate because it's so distributed and there are various processes that are happening that can affect how much ammonia is emitted. I think other thing is also that the nighttime chemistry is still kind of rudimentary. It needs more development and it needs more observational constraints than what one campaign can give us. So there's a lot more work that can be done with the nighttime chemistry, especially the multi-phase chemistry that's happening on aerosols in clouds.
Other questions? Well, let's thank Viral again.
Thank you. Thank you very much.